Let's go ahead and talk about today's warm-up. So I'm going to ask you to redirect your attention this way. If you're still working on it, that's okay, but I do need you to stop talking so that we can go over it. If you want to keep working, that's fine. We are going to be taking notes today after the warm-up on wave behaviors, specifically reflection and interference. So you should have some paper out. You will need to write some things down. This is probably not something that, well, reflection maybe, but interference is probably not something you're super familiar with. And you are going to have an assignment over it as well, 1302.2 interference problem set. So let's go ahead and go over the warm-up question first, and then we can get into the notes for today. It says, a dolphin's sonar system emits waves with a frequency of 2.0 times 10 to the fifth hertz. The waves travel at 1,500 meters per second. What is the wavelength of the wave? So we're going to use the equation that we learned last week. We learned an equation for wave velocity. If you label the information that's in the question, you're going to see that that's the equation that you need to use. So I would start by labeling. My frequency, you can leave it in scientific notation if you like, or you can put it in standard form, which is what I did. 2.0 times 10 to the fifth hertz is 200,000 hertz. And then we have a velocity of 1,500 meters per second. And so you need to have those two pieces of information that were given to you. Of course, we are looking for wavelength. And so if I look at this equation, I know that velocity equals wavelength times frequency. I wrote it on my board over there as well, but it should be in your notes from last week. And so I can tell that if I use this equation, I can solve for wavelength. I am going to substitute in. I am going to have to rearrange some things. Now, if you leave this in scientific notation, then you do need to be careful when you are actually solving it, because depending on how you type that in, you may end up giving yourself the wrong answer. If you type it in so that it's a fraction, 1,500 over 200 or 2.0 times 10 to the fifth, again, if it's still in scientific notation, if it's written as a fraction, you'll be good. Or if you group that whole denominator in parentheses, you'll be good. But if you type it in as 1,500 and then divided by and then 2 times 10 to the fifth, and you don't use parentheses and you don't have it listed as a fraction in that calculator, then it's only going to divide by 2, and then it's going to multiply by 10 to the fifth. Okay, so just make sure that you're careful if you leave it in scientific notation. When you divide this, 1,500 divided by 200,000, if you do it this way, you don't have to worry about that. You get 0.0075, and my unit will be meters. Okay, because that was the length or distance unit in this velocity. The hertz cancels the seconds. So meters is the unit that is remaining. This is the answer to your warm-up, so please make sure that you have entered this in for today's warm-up in My Open Math. And as I said, we're going to get right into it with some notes today as we talk about wave behaviors. Specifically, we're going to talk about reflection and interference. But what am I talking about with wave behaviors? So, wave behavior at a boundary. As waves travel through a medium, they will encounter an obstacle or a new medium to enter into. This is all kinds of waves. I'm speaking right now. That means I am emitting sound waves, and those sound waves that I'm making eventually make their way to your ear and your eardrum or to the wall. They're going to encounter something, some kind of obstacle. We call that a boundary. Okay, where we go from air into whatever, or whatever the boundary may be. It doesn't have to be sound traveling in air. It could be ocean wave moving through water. But if it encounters a new medium, okay, then that's going to be your boundary. The place where one medium ends and another begins is referred to as the boundary, and the behavior of the wave at the boundary is described as boundary behavior. Okay, I'm not too worried about that definition, but we do want to talk about the specific boundary behaviors that you guys are responsible for knowing. We're not going to talk about all of these today, apart from what's on this slide. We are going to go into it some more tomorrow as well. But there are 4 possible boundary behaviors if you want to list them all out for right now, and you can leave some space to add to it because we are going to have some additional notes or however you want to do that. But those 4 possible boundary behaviors are reflection, which is going to mean that the wave is going to bounce off of the boundary. It's going to reflect back. Diffraction, which would mean that it's bending around that obstacle, whatever it may be, without actually crossing through the boundary. Transmission is crossing of the boundary into the new material, so when it actually goes through, it transmits through. And when that happens, sometimes we also have this refraction. Refraction occurs along with transmission and is characterized by a subsequent change in speed, wavelength, and often a change in direction as well. Okay, so those are the boundary behaviors, and as I said, we're going to focus on the first one today, reflection, and what happens when you have a wave reflect, and we're going to talk about interference. So again, we are going to go into these other ones, diffraction and transmission and refraction, more tomorrow. But let's talk about reflection today. So again, you already have that basic definition written down, but you can add to it. The change in direction of a wave at a boundary so that the wave returns into the medium from which it originated. When sound travels in a given medium, it strikes the surface of another medium and bounces back in some other direction. And the direction that it bounces back in is also predictable because we have something called the law of reflection. And the law of reflection simply states that the angle of incidence is equal to the angle of reflection. And you can see here a picture of that. You have an incident ray, so that's the initial, whatever type of wave, sound wave that I'm making, let's say bounces off of the wall. It's going to bounce back at a certain angle depending on the angle at which it strikes the wall. Of course, you've heard sound bounce back before. If you're in a large enough space, if it's far enough away, you'll hear that as an echo. Okay, but that would be a reflection. But here's my angle of incidence labeled here, theta sub I, and angle of reflection labeled here, theta sub R. These will be equal to each other according to the law of reflection. So again, you can add that. Angle of incidence is equal to angle of reflection, maybe even sketching a picture if you like. But this is just showing that this wave, whatever angle it strikes the surface at, it's going to leave at the same angle. All right, so I've talked very briefly about all of these, but let's go ahead and see if we can determine which boundary behaviors we see in each of these examples. This is the first example, and it says, do we see reflection? Now I'm going to, again, make it a little easier. Do you see a wave bouncing off?
Yes.
Yes, okay. So we have reflection. Okay, what about diffraction again? Do we see a wave bending around the obstacle?
No.
In this case, no, it doesn't go around the wall, so no. Okay, transmission, do we see the wave go through the wall?
Yes.
Yes. Okay, and then refraction, again, do we see the wave change direction, velocity, and or wavelength when it passes through? Is it going a different direction or a different speed on the other side of the wall?
No.
It's going a different direction, for sure, because it's striking the wall at some angle and then it's leaving the wall at a different angle. Okay, so yes, we do see refraction. It's hard to tell if it's changed in any other way. Maybe it has. This isn't the best example to look at for that, but definitely you can see a change in direction here. All right, here is ocean waves striking an island, kind of. It's like a little simulation of it. So again, let's go through these. Do we see, and you might have to wait till it starts over, but do we see reflection? Does this wave bounce off? Watch it hit it right here. Does any part of this bounce backwards?
Yes.
Yeah, there's a ripple going backwards right here. You can watch it. Okay, so yes, we do have reflection here. Okay, what about diffraction? Does it bend around the obstacle?
Yes.
Yes. Okay, we couldn't see that with the other one, but you can absolutely see a diffraction pattern on the other side right here. Transmission, does it go through the island?
No.
No. Okay, and then refraction, that's not going to be applicable here because if you don't have transmission, you can't have refraction. That only happens when it passes through. Okay, so again, different types of waves can do different things. Obviously, an ocean wave is not going to go through an island, so you're not going to see transmission and refraction, but sound absolutely can do it, like in the last example. Okay, or you could talk about something even more simple. Here's just a wave pulse on a string, kind of like the FET that you did, except they took a small string and they tied it to a thicker rope or something, And they're doing the same thing you did in the FET, but when it reaches a new medium, which would happen right here at this boundary between the two, we're now going to look at whether we see each of these. So do we see reflection? Does it bounce off? Does it bounce backwards? Yeah, part of it does right here. This part goes backward. Okay, so yes. Diffraction, does it bend around? That's not going to be applicable here because it's in a rope. But let's talk about transmission. Does it go through? Obviously it does. Part of it continues moving forward. You can see a wave pulse in this thicker rope. Okay, so yes. And then refraction, do we have a change in direction, velocity, and or wavelength? Okay, and if you watch this, we don't have a change in direction, and it might be hard to tell velocity or wavelength, I don't know, but if you look at this and you think that it's moving slower, which it kind of looks like it does, okay, then you could say yes. Again, I would give you a more clear-cut example, obviously, if you were answering it on a test, but if you have any of those things changing, direction, velocity, and or wavelength, whenever something is transmitted, you're going to say yes, it does have refraction. All right, so let's talk about with a rope specifically. You can have fixed end reflection. Now, if we had set up our simulation the other day when you ran the FET, and maybe you did this, if you had not changed it to like no end, and you had left it at a fixed end, there was like a clamp at the end, the wave does reflect backward and it gives you these crazy patterns, and some of you were playing with it and I saw that on your screen, so you've already seen this idea. But if you haven't, you're welcome to go look at that FET again and play around with it a little bit so you can see this. But this is talking about fixed end reflection. You're going to have this if you have a string or a rope where you're putting a wave pulse through it, just like we did in the FET, except the end of it's tied off to something, so it's fixed. The end can't move. Okay, and so it says the end of the medium cannot be displaced. For example, a rope that is tied to a pole. Behaviors of a reflection at a fixed end. Okay, so if we had done that, and again, you're welcome to test it out in the FET, if it was fixed, then the reflected pulse will be inverted. So here's the original wave pulse moving toward the boundary, and whenever it reflects, it flips so that it's upside down from what it was before. So that's what this means. Reflected pulse is inverted. The speed will stay the same. The wavelength will stay the same. The amplitude is, again, going to be less than the initial amplitude because you're going to lose some energy right here. If it was a perfect world and it didn't do that, then I suppose you could say that it's the same. But in the real world, your amplitude would be less than the initial amplitude because of the energy loss at the end whenever it's tied off like that. Okay, so again, fixed end reflection, these are some characteristics of that, and that is something you can play around with in the FET if you want to go back and look at it, so you can see it in action. Okay, so I mentioned that we were going to talk about interference, and the reason that I had you guys set up the FET the way that I did without any reflection is because if we hadn't, you would have gotten these crazy wave patterns, and again, if you played with it, you may have seen that, because you're going to get interference of the waves in that medium. Wave interference is the phenomenon that occurs when two waves meet while traveling through the same medium. And if you have a string that's fixed to a wall or something, and you keep oscillating it, yes, you have the waves you're making, but now you also have waves that are reflecting backwards, and the two are going to start to overlap, and you're going to get some kind of wacky looking interference pattern, probably. We'll talk about other ways that can look, but a lot of times whenever you're doing that, you're going to get something that's kind of asymmetric like this. You can see if you look at the background of this animation, in the background there is a blue wave traveling to the right across my screen, and there's a red wave traveling to the left across my screen. And this black wave that you see here is meant to show what happens when the two overlap, whenever the interference occurs between those two waves that are traveling in that same medium. Okay, now before we can really talk about wave interference and different types of interference, we do need to talk about another term that you need to be aware of, and that is phase. Okay, phase specifies the location or timing of a point within a wave cycle of a repetitive wave form. It is used to describe location within a single wavelength. 2 points are said to be in phase if they represent the same position within a wave cycle. Okay, you could even just write down that last sentence there if you wanted to, but we are looking at the specific point or timing within a waveform, and if you have 2 points that are at that same point in the wave, then they're said to be in phase. Okay, so let's see if we can look at some different points on this wave. You'll see a wave down here with a lot of points labeled P through X. Okay, and I'm just asking you, are they in phase? So if we compare point P and point R, are they in phase? Now they are both at equilibrium. Okay, that is true. That does not mean that they're in phase. In order for those points to be in phase, they need to be at the same position within the waveform, and they're not. Although they are both at equilibrium, if you look at point P, it is at this point where the wave is moving toward this crest, and this one's toward a trough. So those are not going to be in phase with one another. They don't represent the same point within the waveform. Okay, if you compare Q and S, are those in phase? Q and S. No, that one's a little easier because one of them's at a crest and one's at a trough. They're obviously not in phase. Okay, T and U, again, they're the same distance from equilibrium, but that's not what that means. Those are not in phase either. Okay, what about R and V? Are those in phase?
Yes.
Yes. Okay, those are both at equilibrium. Okay, and they also represent the same point within the wave cycle. If you can take one point and measure from that point to the next point that I've listed here, and you have a whole number of waves, like one full wave or maybe 2 full waves, it doesn't matter. If it's a whole number of waves, you're in phase. Okay, so R and V are in phase. What about P and V? Here's P, here's V. Are those in phase? No, because that's not a whole number of waves. They represent a different point within the waveform. Okay, so no. T and X? Yes. Okay, those are in phase. They represent the same position within the waveform. Okay, so we need to know that because whether the waves are in phase when they overlap or not is going to determine the type of interference that occurs. Multiple waves are in phase if their crests and trough line up. If they are out of phase when they don't line up, and they can be 180 degrees out of phase if they line up completely opposite each other. So if the crest of one and the trough of the other line up. Okay, we would call those 180 degrees out of phase. When 2 waves are in phase and experience interference, they add up with one another. But when 2 waves are exactly opposite or 180 degrees out of phase and they experience interference, they completely cancel each other out. Okay, either partially or completely, depending on the waves that we're looking at. So let's take a look. Here is an image that kind of shows what I'm talking about. If these 2 waves, ignoring this bottom part right now, if these 2 waves right here were to overlap and be in the same medium at the same time, they would be in phase. They have a trough lined up with a trough, they have a crest lined up with a crest, and they would have what is called constructive interference. They would build on each other. Okay, think construction, build. Okay, but constructive interference. And so these 2 troughs, when they line up, give you an even lower trough. These 2 crests, when they line up, give you an even higher crest because they're building on each other. On the other hand, if the 2 are 180 degrees out of phase or completely opposite, so that the trough of one lines up with the crest of the other, okay, then they are actually going to completely cancel one another out, and you get destructive interference. They destroy each other, if you will, but you get destructive interference if you have them 180 degrees out of phase. And if they're exactly the same size, they have the same amplitude, same wavelength, all of that, you'll actually get complete destructive interference and you have no more waveform at all. Okay, so you can see that there. That, by the way, is how noise canceling headphones work, if you weren't aware of that. They actually will play a sound that completely has complete destructive interference with the surrounding ambient noise. That's how they're designed to work. Some of them work better than others, but that is what they're designed to do. All right, so let's talk a little bit more about constructive wave interference. It is a type of interference that occurs when 2 interfering waves have displacement in the same direction. i.e. both have positive amplitude or both are negative at the same time. The result is a wave with a greater amplitude than either of the two interfering waves because you add their amplitudes together. We just talked about this on the last slide as well, but if you want to add to your definition, you can. But you're going to get this if you have waves that are lined up in phase, where crests line up with crests and troughs line up with troughs. You're going to add them together. If you look at the image in the background with these blue and red waves, you see the blue wave traveling to the right. You see the red wave traveling to the left. This could happen if you have a wave in a medium that reflects backwards and they just happen to align perfectly in phase. You will get this type of motion where crests line up with crests, troughs line up with troughs, and then there's also points here, we'll talk more about these later, where you have destructive interference. But you can see, definitely can see constructive interference at those other points in between. Okay, so if you focus on this point right here and maybe at, let's say, that position, again, you can see what I'm talking about. Crests are lined up pretty much right here, and so you get an even higher amplitude than you had before because you add them together. Okay, destructive wave interference, and you'll notice it's the same picture. That's because I have both happening in this image. It's a type of wave interference that occurs when two interfering waves have displacement in opposite directions, meaning that one of them has a positive amplitude while the other is negative at the same time. The result is a wave with a smaller amplitude or zero than the initial waves. You need to subtract the magnitudes of their amplitude. Again, if we take a look at one of these points, maybe this one right here, okay, and we've paused that wave, okay, at a certain point, you can see that there is a crest here lined up with a trough here, and you get this destructive interference. They cancel each other out. Okay, in this case completely, and that point does not move on the wave. All right, so if you look at this animation, it says look at the amplitudes of the two waves on top and compare it to the amplitude of the resultant wave at the bottom. So this is showing, again, same idea, interference between these two waves, and then down here is showing the resulting wave that would occur as these move the way that they're shown here. Okay, so we see constructive interference, meaning we add them together anytime that they're in phase where the crests align, like right now. Okay, and it's going to do it again right now. Okay, but if they're in phase and their crests align. Destructive interference, on the other hand, you're going to see when they are out of phase, when one crest aligns with the other trough. And again, if you watch the animation, it's about to happen right now, and you see it down here where there's no wave at all at that instant. Okay, but this is basically what's happening. Again, constructive interference, crests with crests, trough with troughs, and you get an even more intense wave with a greater amplitude. Over here we have crests align with troughs and vice versa, troughs with crests, and again, that's going to cancel out. Okay, so how you might see this show up in a question, okay, because obviously hopefully you understand what we're talking about at this point, but how does it look in a question? So it says the diagrams below show two pulses traveling toward each other and the moment where they are superimposed on each other. So superimposed is going to mean that they're overlapping. So if you see that word, it just means one of them is on top of the other one. It says sketch the resultant of the two waves during the interference and indicate if it is constructive or destructive. So if I have these two wave pulses that are shown here to the lower left, moving toward one another, they're going to overlap, okay, like this. Okay, but what's that going to look like? First of all, is this going to be constructive or destructive interference?
Destructive.
Which one? Sorry, I didn't hear which one you said.
Destructive.
All right, well, let me ask you this. Are they going in the same direction or opposite directions?
Opposite.
I don't mean directions this way. I mean the displacement of the medium. They're both displacing the medium upward, right? Both of these show a crest. Okay, I do know they're moving oppositely horizontally. That's not what I'm referring to. Sorry. Okay, these both have the same type of displacement. So if a crest overlaps with a crest, we already said that, we're going to get constructive interference here. Okay, and so when the crests overlap, you're going to get an even taller wave. So this isn't what the resulting wave looks like. Rather, you would add them together. I don't have units labeled here or anything or numbers, but if these are each 1 block tall, well, guess what? The resulting wave is going to be 2 blocks tall. You literally just add them together. Okay, so that would be an example of constructive interference, and that would be what your resulting wave would look like during the time that they're superimposed. Okay, what about here? Again, I have these two waves moving toward one another. Is this going to be constructive or destructive interference? Destructive. Now the displacement of my medium is opposite. Yes, they're still moving toward each other, okay, but I'm looking at the displacement of the medium. One's down, one's up. Okay, and so during interference, when they overlap, again, you're not going to see this. You're going to see what happens when the two add together. Well, this is -2 blocks. This is +1, so the resulting wave is going to look like that. Okay, with the height of -1. Again, whatever these units are. Okay, so again, that would be an example of destructive interference. So these have some numbers put to it. Might make it a little bit easier. So same thing. It wants to know if this is going to be constructive or destructive interference. So let's start there. Constructive. Okay, because they have displacement in the same direction while they're moving toward each other. So they will overlap, and when they do, you're going to add these together. This one's -20, this one's -10. So when I add them, my resulting wave will be -30, or have an amplitude of -30. Okay, and so again, that's all I did. -10 plus -20 is -30. Okay, but that is constructive interference because they're in the same direction. Okay, this, now I have two waves moving toward each other, again, through the same medium, but this is going to be destructive interference. Okay, they're going to cancel each other out, at least partially. If they were the exact same height, by the way, they would completely cancel each other out. Okay, they're not, so you're not going to get complete destructive interference, but this time I have -15 and +5, and so the amplitude of that's going to be -10. Okay, 5 plus -15 is -10 centimeters, and that would be what my resulting wave would look like. That is due to destructive interference because they are displacing the medium in opposite directions. Are there questions about this? I think it's pretty straightforward, but I just want to make sure. Okay. All right, good, because that's what you're working on for the rest of the period today. So if you will make your way to My Open Math, you have an assignment, 1302.2, wave interference problem set. If you don't finish it during the class period today, it is due by 11:59 p.m. tonight. I believe this one's going to take you to a digital simulation, at least for a portion of it. It might be the whole thing, to actually practice with some of this as well so you can see it. But go ahead and get to work. Obviously, if you don't finish it here, make sure that you finish it for homework. And if you have questions as you're working, please let me know.